Lecture 1. System, Surroundings, Heat, and Work. A thermodynamic system is the specific part of the universe we choose to study. It could be a chemical reaction, a solution, or a gas inside a container. Everything outside the system is called the surroundings. This includes the container, the air, and any equipment in contact with the system. Energy can move between the system and the surroundings in two main ways. Heat, represented by Q, is energy transferred because of a temperature difference. Work, represented by W, is energy transferred when a force causes movement. Temperature is different from heat. Temperature measures the average kinetic energy of the particles. Heat describes energy moving from a warmer object to a cooler object. Clearly defining the system is important because the signs of heat and work depend on whether energy enters or leaves that system. Lecture 2. Open, closed, and isolated systems. Thermodynamic systems can be classified as open, closed, or isolated. An open system can exchange both matter and energy with its surroundings. An uncovered beaker is an example. Water can evaporate, matter can enter or leave, and heat can also be transferred. A closed system can exchange energy, but not matter. A sealed flask is a good example. Heat can pass through the walls, but the particles inside cannot escape. An isolated system exchanges neither matter nor energy. A perfectly insulated and sealed container would be an ideal isolated system. Real calorimeters are designed to behave as closely as possible to isolated systems. However, perfect insulation is impossible, so some heat may still escape. When analyzing an experiment, first identify which type of system is being used. This determines which energy and matter transfers are possible. Lecture 3. Heating and cooling curves. A heating curve shows how temperature changes as heat is added to a substance. The slope sections represent temperature changes within a single phase. The particles gain kinetic energy, so the temperature rises. The horizontal sections represent phase changes. During melting, solid and liquid exist together. During boiling, liquid and gas exist together. Temperature remains constant during these phase changes because the added energy is used to overcome interparticle attractions. It increases potential energy rather than average kinetic energy. A cooling curve shows the reverse process. Gas cools and condenses. The liquid then cools and freezes. During condensation and freezing, energy is released to the surroundings. The temperature remains constant while the phase change occurs. The length of each plateau depends on the amount of substance and the molar enthalpy of the corresponding phase change. Lecture 4. Endothermic and exothermic processes. An endothermic process absorbs heat from the surroundings. Heat moves into the system, so delta H is positive. Because energy is removed from the surroundings may become colder. Melting, vaporization, and many thermal decomposition reactions are endothermic. An exothermic process releases heat to the surroundings. Heat moves out of the system, so delta H is negative. The surroundings may become warmer because they receive this released energy. Freezing, condensation, combustion, and many neutralization reactions are exothermic. On an energy diagram, the products of an endothermic reaction are higher in energy than the reactants. For an exothermic reaction, the products are lower in energy than the reactants. Remember that delta H is always defined from the system's perspective. Energy entering the system gives a positive value. Energy leaving the system gives a negative value. Lecture 5. Energy of dissolution. Dissolving an ionic compound can be separated into three energy changes. First, the ions must be separated from the ionic lattice. This requires energy, so the lattice separation step is endothermic. Second, some solvent molecules must be separated to create space for the ions. This also requires energy and is endothermic. Finally, the separated ions become surrounded by water molecules. This process is called hydration. Ion dipole attractions form between the ions in water, releasing energy. The oxygen side of a water molecule points toward positive ions. The hydrogen side points toward negative ions. The overall enthalpy of solution depends on the balance between the energy absorbed during separation and the energy released during hydration. If hydration releases more energy than separation requires, dissolution is exothermic. If separation requires more energy, dissolution is endothermic. Lecture 6. reaction energy diagrams. A reaction energy diagram shows how potential energy changes as reactants become products. The vertical axis represents potential energy. The horizontal axis represents reaction progress. It does not represent time. The highest point on the curve is the transition state. The energy difference between the reactants and this peak is the activation energy. For an exothermic reaction, the products are lower in energy than the reactants. Delta H is negative because energy is released. For an endothermic reaction, the products are higher in energy. Delta H is positive because energy is absorbed. Activation energy and delta H describe different things. Activation energy affects how quickly a reaction can occur. Delta H describes the overall energy difference between products and reactants. A catalyst lowers the activation energy by providing another pathway. However, it does not change the energy of the reactants, the energy of the products, or delta H. Lecture 7. Thermal energy and molecular collisions. Temperature measures the average kinetic energy of particles. Particles in a hotter sample have greater average kinetic energy. They generally move faster and collide more energetically. Particles in a colder sample have lower average kinetic energy and move more slowly on average. When hot and cold objects make contact, collisions transfer energy from the faster particles to the slower particles. This energy transfer continues until both objects reach the same temperature. This condition is called thermal equilibrium. At thermal equilibrium, particles are still moving and colliding. However, there is no net heat transfer because both objects have the same average kinetic energy. Heat flows spontaneously from a higher temperature to a lower temperature. It does not naturally flow in the opposite direction without an external energy input. Temperature describes particle motion, while heat describes energy being transferred. Lecture 8. Conservation of energy. Energy cannot be created or destroyed. It can only be transferred or converted from one form to another. This is the first law of thermodynamics. If a chemical system loses energy, the surroundings must gain the same amount. If the system gains energy, the surroundings must lose the same amount. This relationship can be expressed by saying that the heat gained or lost by the system equals the negative of the heat gained or lost by the surroundings. For an exothermic reaction, Q of the system is negative because the system releases heat. The surroundings gain that energy, so Q of the surroundings is positive. For an endothermic reaction, Q of the system is positive. The surroundings lose energy, so Q of the surroundings is negative. The total energy change of the system and the surroundings together is always zero. Calorimetry calculations are based directly on this conservation principle. Lecture 9. Internal energy and the first law. Internal energy is the total kinetic and potential energy of all particles inside a system. We usually cannot measure the absolute internal energy. Instead, we measure the change in internal energy, called delta E. The first law can be written as delta E equals Q plus W. Heat entering the system makes Q positive. Heat leaving the system makes Q negative. Work done on the system makes W positive. Work done by the system makes W negative. For example, if a gas expands and pushes a piston upward, the gas does work on the surroundings. Therefore, W is negative. If the surroundings compress the gas, work is done on the system, so W is positive. To calculate delta E correctly, identify the direction of both heat and work before substituting any numbers. The sign convention always uses the system as the reference point. Lecture 10. Heat transfer. The heat transfer during a temperature change can be calculated using the equation Q equals m times C times delta T. In this equation, Q is the heat transferred, m is the mass. C is the specific heat capacity. Delta T is the final temperature minus the initial temperature. When a hot metal is placed in cooler water, the metal loses heat and the water gains heat. Assuming no heat escapes, Q of the hot object plus Q of the cold object equals 0. The metal's temperature decreases, giving it a negative delta T. The water's temperature increases, giving it a positive delta T. Eventually, both reach the same final temperature. Do not assume that they experience equal temperature changes. They transfer equal amounts of heat, but the temperature changes depend on their masses and specific heat capacities. Always include the correct sign for delta T. Lecture 11. Specific heat capacity. Specific heat capacity is the energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Water has a specific heat capacity of approximately 4.184 joules per gram per degree Celsius. Aluminum has a lower specific heat capacity, and copper has an even lower value. If equal masses absorb the same amount of heat, water experiences the smallest temperature increase. Copper experiences the largest temperature increase. This follows from the equation Q equals m times C times delta T. When Q and M are fixed, a larger value of C produces a smaller delta T. Water's high specific heat capacity allows it to absorb large amounts of energy without changing temperature dramatically. This property helps regulate environmental temperatures and makes water useful in calorimetry. Specific heat capacity is a property of a substance, so different materials respond differently to the same energy input. Lecture 12. Coffee cup calorimetry. A coffee cup calorimeter is used to measure heat transferred during a reaction in solution. 2 nested foam cups provide insulation. A lid reduces heat exchange with the surroundings, and a thermometer measures the temperature change. The solution is stirred to maintain a uniform temperature. The heat absorbed by the solution is calculated using the equation Q of the solution equals m times C times delta T. The reaction and the solution exchange equal amounts of heat with opposite signs. Therefore, Q of the reaction equals the negative of Q of the solution. To calculate the molar enthalpy, divide the reaction heat by the number of moles of the limiting reactant. If the solution temperature rises, the solution gains heat, so Q of the solution is positive. The reaction released that heat, so Q of the reaction and delta H are negative. If the temperature falls, the reaction is endothermic. Lecture 13. Heating curve calculations. Different sections of a heating curve require different equations. During a sloped section, the substance remains in one phase and its temperature changes. Use the equation Q equals m times C times delta T. During melting, the temperature remains constant. Use the equation Q equals n times delta H of fusion. During boiling, use the equation Q equals n times delta H of vaporization. A complete heating problem may include warming the solid, melting it, warming the liquid, boiling it, and warming the gas. Calculate the energy for each section separately. Then add all the values to obtain the total heat. Do not use Q equals m times C times delta T during a phase change plateau because the temperature does not change. Also make sure that you use the correct specific heat capacity for each phase. The solid, liquid, and gas may have different values. Lecture 14. Calorimetry errors and improvements. Real calorimetry experiments are not perfectly isolated. Heat loss to the surroundings reduces the measured temperature change. This usually makes the calculated magnitude of delta H too small. Incomplete combustion also releases less heat than expected. Evaporation can carry energy away from the calorimeter. A thermometer may respond too slowly, causing the highest or lowest temperature to be missed. The calorimeter itself can absorb heat. If this energy is ignored, the calculated reaction heat will be underestimated. Accuracy can be improved by using a tight-fitting lid, better insulation, continuous stirring, and a calibrated thermometer. The calorimeter's heat capacity can also be measured and included in the calculation. Repeating the experiment and averaging consistent results improves reliability. However, it does not automatically remove systematic errors. Lecture 15. Standard enthalpy changes. Standard enthalpy changes are measured with substances in their standard states at a pressure of 100 kilopascals. Solution concentrations are normally 1 mole per liter. A temperature such as 298 Kelvin is usually specified. Standard enthalpy of reaction refers to the enthalpy change for a reaction exactly as written. Standard enthalpy of formation is the enthalpy change when 1 mole of a compound forms from its elements in their standard states. Standard enthalpy of combustion describes the complete combustion of 1 mole of a substance in oxygen. Standard enthalpy of neutralization describes the formation of 1 mole of water from an acid-base reaction. The small circle next to the delta H symbol indicates standard conditions. Physical states must always be included because enthalpy depends on whether a substance is solid, liquid, gas, or aqueous. Lecture 16. Thermochemical equations. A thermochemical equation includes both a balanced chemical equation and its enthalpy change. the enthalpy value applies to the reaction exactly as written. For example, forming 1 mole of liquid water from hydrogen and oxygen releases 286 kilojoules. If the entire equation is reversed, the direction of energy transfer also reverses. The sign of delta H must change. The reverse decomposition of water, therefore, has a positive delta H of 286 kilojoules per mole. If all coefficients are multiplied by 2, delta H must also be multiplied by 2. This happens because twice as much matter reacts and twice as much energy is transferred. Physical states must remain consistent. Producing water vapor instead of liquid water would have a different enthalpy change. Treat delta H as part of the chemical equation. Lecture 17. Bond breaking and bond formation. Breaking a chemical bond always requires energy. Bonded atoms are in a relatively stable, low potential energy arrangement. Energy must be absorbed to separate them. Bond formation has the opposite effect. When separated atoms form a bond, potential energy decreases and energy is released. The overall reaction enthalpy depends on both processes. A useful relationship is this. Delta H of the reaction equals the energy absorbed to break bonds, minus the energy released when new bonds form. If forming the product bonds releases more energy than bond breaking requires, delta H is negative and the reaction is exothermic. If bond breaking requires more energy than bond formation releases, delta H is positive and the reaction is endothermic. Never say that breaking bonds releases energy. Bond breaking is always an energy-absorbing process. Lecture 18. Enthalpy from bond energies. Average bond enthalpies can be used to estimate a reaction's enthalpy change. Consider hydrogen gas reacting with chlorine gas to form hydrogen chloride. One hydrogen to hydrogen bond and one chlorine to chlorine bond must be broken. This requires 436 plus 243 kilojoules per mole. 2 hydrogen to chlorine bonds are formed. Each bond releases approximately 431 kilojoules per mole. Delta H equals the energy of the bonds broken minus the energy of the bonds formed. That gives 679 minus 862, which equals negative 183 kilojoules per mole. The negative result shows that the reaction is exothermic. Bond enthalpy calculations are estimates because the listed values are averages taken from many gaseous molecules. Lecture 19. Standard enthalpy of formation. Standard enthalpy of formation is the enthalpy change when exactly 1 mole of a compound forms from its elements in their standard states. For liquid water, hydrogen gas reacts with 1/2 mole of oxygen gas to produce 1 mole of liquid water. Fractions are acceptable because the definition requires exactly 1 mole of product. The standard enthalpy of formation of an element in its standard state is 0. For example, hydrogen gas, oxygen gas, and graphite each have a standard enthalpy of formation of 0. Reaction enthalpy can be calculated by subtracting the total formation enthalpy of the reactants from the total formation enthalpy of the products. Remember to multiply every formation value by its stoichiometric coefficient. Physical states matter. Liquid water and water vapor have different standard enthalpies of formation. Lecture 20. Hess's Law. Hess's law states that enthalpy is a state function. This means the total enthalpy change depends only on the initial reactants and final products. It does not depend on the pathway taken. A target reaction can therefore be produced by adding other known reactions. Equations may be reversed or multiplied. When an equation is reversed, the sign of delta H changes. When the coefficients are multiplied, delta H is multiplied by the same factor. After arranging the equations, add them together and cancel any substances appearing on both sides. For the formation of carbon monoxide, combining the combustion of carbon with the reverse combustion of carbon monoxide gives an enthalpy change of negative 110.5 kilojoules per mole. The direct pathway and the multi-step pathway must have the same total delta H because they begin and end in the same states.